In the previous video, we learned about vectors in R2 and R3, and those are generally the first types of vectors that people encounter in their lives. They're pretty easy to work with. They are very intuitive on a geometric side of things. You can really see what's going on here. They're also incredibly practical. They're used in physics. They're used in lots of other situations as well. However, it turns out over the years, mathematicians were studying them and said, well, hey, we see some other things that behave very, very similarly to R2 and R3. And it turns out that because they behave similarly, they're going to have a lot of the same properties. And we can use the results for how things like R2 and R3 behave in order to figure out how other stranger things would behave. And in order to do that, they needed to codify, they needed to find a set of properties that would be the defining characteristics of what such a vector idea would be. And then once they decided that, then they looked around and saw what things would have it and what things would not have those properties. So these right here became the definition of what it means to be a vector space. So a vector space is a set, and there are two different things that you're going to be allowed to do in that set. One is going to be called vector addition, one is going to be called scalar multiplication. That should sound familiar. That's the two things we can do with R2 and R3 vectors. And then we need those two operations to satisfy all 10 of these properties. Now, I kind of broke them up here, 1 through 5 and 6 through 10. 1 through 5 only deal with the vector addition operation, whereas 6 through 10 will deal with the scalar multiplication operation. Now, 1 and 6, sometimes these are listed in here, sometimes they are not. If they are not listed, they are implied elsewhere in the problem. These are what are called closure. The idea is we want to be closed, or we want to be able to combine things and end up with something similar. So we want to be able to add two vectors in 2 dimensions and have the answer still be in 2 dimensions. We would not like the idea to have a universe where you could add a 3-dimensional vector and a 3-dimensional vector, and somehow we're now in dimensions 5 and the whole world just kind of fails. So this closure on the left side is that when you're adding vectors, that the answer you get is still the same type of thing you started with. You're still in your set V. On the other hand, the right side, number 6 there, is saying that if you do a scalar multiplication, that the answer you get is still similar to what you started with, still in the V set. Now, number 2 and 3, there's really not much to talk about here. They are showing that either the set is commutative, property 2, or that it's associative, property 3, with regards to vector addition. Number 4 is that there has to be some sort of a 0 vector, that if you add 0 to anything, you get back to what you started with. Number 5, all vectors have to have negatives, versions of them in there, so that you can add them up and get the 0 answer. Basically, we want that to be able to cancel vectors out. If I tell you to travel in one direction, I need to be able to tell you to travel in the opposite direction to get back to where you started from. Over on the right properties, the number 7 here is the associative property for scalar multiplication. Number 8 says that if you multiply by the number 1, you better get back to what you started with. Otherwise, it doesn't really make sense for us. And then 9 and 10, the last two, are just saying you can do distributive property here. And one is you are distributing a constant into 2 vectors, and the other is you're distributing a vector into 2 constants. We're just making sure that both of these will actually work out and give you the answer, or a valid answer, I should say. So I would not necessarily recommend memorizing all 10 of these properties. I mean, obviously you could if you wanted to, but I don't think it's really effective to do so. Anytime you really need these, you can always look them up. But these are the 10 properties here it's more a good idea to understand them and maybe check whether things are not working out on one of these properties. For example, if I told you to multiply matrices, you'd remember that's not commutative, so we wouldn't want to use that here. But regardless, these are just the properties that we've decided that we need in order to be called a vector space. So once we have these properties, let's talk about some examples of things that are in fact vector spaces. So one of which is R2 or R3, or if you want to make it even higher dimensional, Rn here. These are the prototypes for vector spaces. These are the ones you first deal with, and they're the easiest to manage. The next ones here are the set of all m by n matrices. Now you do have to have specific values here, so let's say I do m, 3, 2. Those would be all the possible 3 by 2 matrices out there. And if you have two 3 by 2 matrices, you can add them together and you can get another 3 by 2 matrix. And if you take a 3 by 2 matrix and you multiply it by a constant, you're still going to get a 3 by 2 matrix. That's your closure properties. You can check all the other ones there, or you can believe me that it's going to turn out to be a vector space. It is. And that's one of the things I want to point out now, is that anytime you come across something new, if you want to check whether or not it's a vector space, you have to check all 10 of these things. It can be pretty much a pain. On the other hand, if I were to give you something where I know at least one of the properties is going to fail, that would guaranteed be not a vector space, and it's much easier for me to say, here's an example, show me why it's not a vector space. And then instead of having to find all 10 things and make sure they work, you just have to find the one that doesn't work. It just makes the problem a lot more focused and less tedious when giving them. Now, with that said, we also have some more interesting versions of them. So the next one here is Pn. It's a set of all polynomials of degree less than or equal to n. So for example, P2 is the set of all polynomials of degree 2 or smaller. And if we have two polynomials, let's say 3x squared plus 5x minus 1, and I can add on to another polynomial, 4x plus 7, and you add them together, and you would get a new polynomial of degree less than or equal to 2. So it does work here. The reason why we need it to be less than or equal to 2 is because when you add them up together, maybe the x squared part cancels out. Maybe it does end up getting a smaller degree than degree 2. Also, we need to have the 0 vector in our set, and the 0 vector is not going to have degree exactly 2. So that's why we do less than or equal to degree 2. Regardless, this is what we have here. And then the last interesting one here that I want to talk about in this video is the set of all functions, and you can pick whatever domain you want here. Considering a lot of the functions we deal with in math class has domain all real numbers, that's what I chose. I chose having domain all real numbers here. And so, for example, if you have the function f of x is e to the x, and g of x is, I don't know, square root of x, no, sorry, I want to make it right domain, right? So let's make it cube root of x. Then these two functions here both have domain all reals, and we can add them together, and we still have a function whose domain is all reals. And this is really showing you how weird things can get, because, in R2 and R3, we were very easily able to see what a direction would mean there. What is the direction on an associated to a given problem, 2, 3, or whatever. But now, what is the direction of e to the x? That doesn't really make any sense. And so now we can start seeing, weird things that don't really mean directions anymore, but they are still going to be considered vectors. Just shows you that there's a much broader perspective that we have on a class like this.